Robots in collaborative environments must adapt both motion and compliance to task demands. Achieving this requires generalizing learned behaviors to new settings while ensuring stability. We use dynamic movement primitives for motion generation and variable impedance control for compliant interaction. DMPs combine a stable goal attractor with a shaping term called the forcing function. While they generalize well to new goals, they struggle with complex motions. Using model-free learning, we can enable complex trajectory adaptation while preserving DMP stability by parameterizing only the gated forcing function, which decays near the goal. This also reduces the search space. While the forcing function shapes path, the impedance profile governs how it's executed. But learning these gains is delicate. Unconstrained sampling can destabilize behavior, even if the motion is valid. C-GMS addresses this by optimizing both trajectory and impedance, with guarantees on stability and actuator feasibility. Gains are derived from constrained slacks, satisfying Lyapunov conditions. A torque governor scales them to respect actuator limits without breaking the certificate. With both components parameterized, we optimize them using PI2 over task rollouts. Let's see how this performs in collaborative settings. Our first task imagines a simple but familiar scenario: a robot delivering food to a hungry collaborator. In the nominal case, there are no obstructions. Now we introduce an obstacle into the workspace. C-GMS adapts the trajectory to avoid it, while modulating impedance to remain both compliant and safe. In the next task, the robot assists a person who's focused on their work by handing over a pen stand. Again, the nominal execution follows an obstacle-free path. With an obstruction introduced, C-GMS once again adjusts the trajectory while maintaining certified stability. The impedance adapts locally, remaining compliant throughout the motion and increasing stiffness only when necessary. Now we show what happens without stability constraints. Sampling from unsafe regions causes erratic motion. The robot violates joint limits and moves unpredictably close to the human before triggering a safety lockout. We now highlight generalization. Across 4 different tasks, C-GMS produces stable and feasible behaviors without any task-specific tuning.